Okay, so this is the very last video that I'm recording for this year's version of XM. So I'm returning to the question of how does guessgf work. So guessgf is the tool that we've used sometimes with success to recognize sequences of numbers, mainly sequences of integers. And when we discussed this back just before Christmas, I promised that I would get back to you and explain roughly how this works. And this is what is going to happen now. So the basis of this idea is to look at rational functions. So the idea is that whenever you have um, power series is what we have, right? We have some numbers, C0, C1, C2, and so on. We use it to make a power series, and we only have some of these C's given, and then sort of imagine that the rest of them are given in some systematic way. Then it's a general mathematical fact that actually there's a very large family of numbers that define power series this way that turn out to sum two rational functions. And a rational function is just a fraction between two polynomials. And I will talk about an m over n rational function where m is the grade that I have, the degree that I have in the the numerator, and n is the degree that I have in the denominator. So, and also there's sort of a scaling condition that makes me decide that b0 is always 1. So that's sort of a standard way of doing this. So that also ensures that I'm not dividing too much with 0. So, so the point is that, and this is the Pade approximant idea that says that suppose that you have a function, just any function which is significantly differentiable. So let's say that it's differentiable up to order m plus n plus 1. Then there is a unique rational function that has the property that it matches up with the derivatives of f. Right? So I mean, of course, you're very familiar with this. If n is 0, so if n is 0, then it's just I'm asking, is there a polynomial that matches up with f on the first I derivatives? And of course, the answer to that is sure, you can look at the Taylor polynomial. But the idea is to look at a fraction instead, and you have the freedom of putting some weight in on top and some weight below, and there's a sort of a freedom here. And this is the so the statement here that there's one and only one of these choices. So it says, to be more precise, suppose that we have a function f, it's differentiable enough, then for any m and m, so that we have enough derivative of f, then we can choose the q in a unique way so that it matches up. And I mean, the fact that this is true is fairly straightforward, but the point of the Pade approximation theory, which is frankly not something I had ever heard about before I looked at guessgf, it's something that's quite important in certain branches of physics. But the idea is that not only is there such a function, there's also a very efficient way of finding it. So the Pade approximant is it's a nice choice of a function, a rational function that matches up with some given data in a sequence that we think of as the coefficients of a power series, right? And of course, then there's something with a division by n factorial, but that sort of cancels out here. So, and then we say that a Pade approximant is degenerate if the first coefficients here, the am and the bn, if they are 0. And that plays a special role in the theory that I want to show you. So let's go back to Maple and look at an easy example. So what I'm looking at here is now I'm taking, I'm looking at a polynomial which I'm thinking of as sort of first finite chunk of a power series. And the choice that I made here was I took the factorials as the coefficients. And then I'm trying to do a Pade approximant of this polynomial. And you can see I have 9 terms. And the theorem says that if I have 9 terms, then I can find such a choice if the sum of m and n is 8, right? So the relevant number is m plus n plus 1. So I will just say 4, 4. And so I'm looking for the choice of a per day approximant of an expression like this. And what happens here is something which is not very interesting. It sort of gives me a per day approximant which is not degenerate. But let's look at another example where I now chose the Fibonacci numbers as my coefficients. And when I do this per day approximation, I get, and this is not surprising, right? We sort of know where this comes from. But the point here is that what I'm getting here is a per day approximant which is degenerate, because I asked Maple for a 4-4 approximation. So I asked for the unique per day approximant that has a fourth order polynomial on top and a fourth order polynomial below. But as you can see, I get something of degree 1 on top and degree 2 on below. So it's actually the 1-2 approximation here, right? So that's the same. So what's happening here is that we're asking for a big per day approximant, one that has many choices for coefficients, but Maple chooses for us, the one that we get has a lot of zeros, right? So that means that somehow we could have gotten this, this choice here, we could have gotten for using only the first 4 terms, but if we use all 9 terms and we ask for the 4-4 approximant, then we get something that is actually smaller, right? So the general way of thinking of this is that, you know, if you have a situation like this, that doesn't tell you anything in terms of symbolic inversion. It's not useful for understanding the sequence that we're after. But if you're getting something here, and the reason is that this is not degenerate, right? I have fourth order terms. But if I do the same here, I get something of lower order, and this then must mean something, right? And if it means something, then you can say, okay, I have this. This is my guess of the infinite sum of this power series, and then you can use this to analyze, in this case, the Fibonacci numbers. And this would work, as we sort of know. So if we take another example that came up, this is from the analysis of various kinds of pyramids. If I ask Maple for something that describes that, then we've seen this before, we actually get a hit, right? So there's a nice function, not as nice perhaps as you would like, that would generate L in the sense that if you compute the first terms of the power series, then you get back the data that you sort of put in. You can see that this expression, however, is not a rational function, right? So this is not, this is a more complicated thing that has some square roots. So the question is, how can Maple recognize this by the help of per day approximation? And the answer is very parallel to what we saw when we looked at, for instance, identify. Right? So identify is really good using the PSLQ algorithm. It's very good at finding sort of linear integer combinations of numbers, right? So it can recognize anything that looks like an integer times pi plus an integer times e plus an integer, something like that. But then we could get much farther by sort of saying, okay, instead of trying to analyze the number itself this way, we can transform the number, like taking its logarithm or whatever, and then if we can recognize that, then we can sort of go back. And the same is it's exactly the same way that guessgf works. So let me just show you in this particular instance how that would go, right? So I'm defining now this function that is given by the data that I have up here. And now I'm asking for the per day approximation of that. Again, I'm taking a 4-4 per day approximation. And as you can see, that's because I have 9 terms. And you can see that this is not degenerate, so it doesn't really give you anything. But then what you can try to do is that you can try to make various transformations of the data. And one transformation that actually works here is to look at the power series that is related to the inverse of the function that we're looking at. Right? So if I have a function and that's given by a certain power series, then you can sort of hope that the inverse of that function, first of all, you can hope that the function is bijective enough. It just has to be bijective close to 0. And then you can hope that the inverse of the function that you're looking at is actually also analytic in the sense that it has a description as a power series. And if that happens, you can compute the power series. There's a straightforward formula, and this is built into Maple, and it's built in actually to the to the GFON package that I'm using here. And so this is the power series that corresponds to looking not at the original function here, but at the inverse of the original function. And then we're lucky, and we can see that actually Maple recognizes that. Right? So you can do this. I mean, sometimes when you do these transformations, you will lose some terms. But here, actually, you can check that you don't lose any terms. And so I can, again, do the 4-4 per day approximation. And you can see I get a hit. I get something that's lower order. Right? So I'll just call that hit. And then you can see when I do the expansion of that, I get exactly the coefficients that I had up here. So I was not able to recognize the original function, but now I can recognize the inverse of that function. And then, of course, I just need to sort of substitute back. And what I have to do is to solve the equation set is the same as this, and then isolate out w in that. And when you do this, you essentially have to solve a quadratic, and you get two solutions, and it turns out that this one is the one that's relevant, and that's actually the same as the one that we have up here. When you can sort of see when you move the terms around. Right, so what happens here, and I'm not going to show you any more of this, but I mean you can sort of see how this goes, right? So Maple will first see if it can recognize your sequence as a rational function using per day approximation, and then it will do sort of a whole barrage of various things that it can do to do some transformations and hope that it can find that as well. And that's how guessgf works. So that is it for now.